Hi.
Hello, everyone. Welcome to MACSMIN 2025. Now, Jack Gallimore will talk about a continuous-based method for classifying alpha helices. Please, Jack.
Yeah, so a continuous-based method for classifying alpha helices using hydrogen bond geometry. So protein structure has already been introduced a few times, so I'll just recap that the primary structure is defined by the sequence of residues of given length n, and the secondary structure forms because of hydrogen bonding between these residues. Structures, which is beta sheets. Alpha helices.
Just a second.
Just a minute.
Okay, can participants online hear us? Do they?
Yes.
Coming out of there, yeah. So just two people have the volume on, or mics.
But can you? Is your camera working?
Yeah.
Yeah.
Is that okay? Yeah, so we see hydrogen bonding between the residues on the two main structures, which are beta sheets and alpha helices. So in alpha helices, we form a coil-like shape, and hydrogen bonds form between every few residues. And in sheets, they form between strands. Now, these strands can be quite far apart. And here we see that there's three main types of helices, and the hydrogen bonds form between every three residues. Every four for alpha helices and every five for pi helices. And again, with sheets, they can form between pretty much any residue. They're just sections of chains that happen to be near each other. So they can be quite far apart. So we get all of our data from the protein data bank, which contains the structural information of the proteins, which also includes the secondary structure labels. There is one label for each residue, which says helices, sheets, or turns. Turns are basically the absence of a proper structure. And these labels are assigned by the authors, leading to variation in the same structures and how they're classified, because they can basically do it however they want. Mainly, they'll use a method called DSSP, which is defined secondary structure of proteins. This is common, but even this standardized method has limitations. This is the formula for DSSP, and this basically is a bunch of distances between atoms, some set constants, and if the threshold of E is overcome, they say a hydrogen bond forms. Oh, again, the problem with this formula is it relies on the location of hydrogen bonds, which, as Mike said before, the hydrogen atoms, which, as Mike said before, can't really be accurately found in proteins. There's also multiple versions of this formula. So you could have each PDB file could use different versions of this. And thirdly, these are pretty ambiguous thresholds with not really much meaning behind them. The aim of this project is develop a standardized continuous method to predict hydrogen bonding. Our approach avoids the dependence on hydrogen atoms too, which is important. And this is a sort of framework we'll use. So we take the distance between the oxygen in residue I and the nitrogen in I plus S, where S is the step. The steps like we see in when we talk about the helices and the hydrogen bonding. And also the angle between the carbon in residue I, the oxygen in residue I, and the nitrogen in I plus S. And that's a little drawing there with the angles and the distances. They're important. And for each of the 700,000 chains and models in the PDB database we developed, we produce a file something like this, which produces distances for each of the step sizes. Now this one shows steps 2, 3, 4, 5, but the newer ones have steps -20 to max +20 to really be quite thorough. And again, we used a clean database that we've talked about a few times, developed by the group switch to so here are some of the heat maps when we here are some of the heat maps we develop when we put all the data for a given step size in a 3D plot. So we see the distance and the angle for a given step size. So for this example, it's step 4. What we see is quite a large peak of low distance between the O and N atoms and an angle of about 155 degrees. Now this large peak is likely because alpha helices are quite common and they form hydrogen bonds in the step 4 space. These sort of distances and angles are what we'd expect to see as laid out by the book of protein biophysics. But this peak in this sort of zone, which we think is telling of hydrogen bonding, isn't just present in the step 4 space. Like for alpha helices, we have step 3 here, which is a slightly lower angle, but we're still in sort of same region. And then
Wait, on that plot, there's sort of another like lesser peak, I suppose.
yeah.
On both of them. Do you know what you can attribute that to?
Well, these are quite high distances and random angles. These are probably just loop or sheet points that don't really have a conformed structure. That's why it's not as consistent.
Yeah,
It's kind of just a general cloud, but you see quite good separation between like the consistent helical sort of bonding and other points. Is that answer your question?
Yeah, sure.
But we can also look at other steps. So this is step 7. Now, this sort of region here is where we see the large peak in other step sizes. Obviously, it's a lot smaller now, kind of overshadowed by this, which is other points. So it's quite consistent, probably longer helices. Obviously, these don't form hydrogen bonds because they are 7 residuals apart. But the fact that this peak appears, even though it's overshadowed, in multiple step sizes, here's step 20, and here's the peak. Speaks to the consistency of the conditions of hydrogen bonding. Does anyone have any questions so far? Yeah.
Can I just double check, is this graph from the whole data set and all of the angle distance?
So the
This isn't just one chain, I mean.
so
Yeah.
step 7 and 15 are actually only for PDB files with a resolution of less than 2 angstroms. I believe these 3 and 4 ones are actually all the PDB ones, which I should have said to be fair. So these are about a 10% subset of the most accurate proteins, whereas these 2 are all residues. So there's about 100 million pairs of points in these 2 and 10 million in them.
The reason that last one has so many peaks is that just sort of randomness, I suppose.
Most of the points have high distance. So if you look at this one, in step 15, it goes up to about a distance of 30, but I've kind of cut it off so you can actually see this area. Most of your points will be over here.
Yeah.
I just cut them off. There's only a few points there because there's not that many step 15 hydrogen bonds. Right, that's the presentation. These are just the pictures of putting. Yeah. Anyway, so if you aggregate the graphs from steps -20 to 20, the maxima, the local maxima in that region occurs at 2.935 angstroms and 2.705 radians, which is about 155 degrees. I said the angles are expressed in radians, so they are of similar value, which will be important for the next bit. And to estimate the likelihood of a hydrogen bond or the strength of a hydrogen bond, we define a hydrogen bond strength function, which between residual I and j is e to the power of minus d, where d is the Euclidean distance between the observed peak laid out here and the point, the pair of I and j. You can combine these bond strengths then to see this distribution. So this will be a distribution of all the bond strengths across steps minus 20 to 20. So there's quite a lot, over 1 billion. But you see a quite nice separation between likely hydrogen bonds here, and then other ones. It's quite good. And there's a minima at about 0.66. Yeah. So maybe you could call that a cutoff to say you think there is one, you think there's not, but that's not that important because it's meant to be a continuous method. So we can now construct an n by n matrix where n is the length of the chain, where each entry for ij represents the hydrogen bond strength between I and j. The resultant n by n matrix provides a global view of hydrogen bond connectivity across the protein. Here's some examples. So, too bad just getting a full file. This is an example for 1HHO, which is hemoglobin. That's quite the common protein. And you've basically got here the carbon and oxygen atom in residual 1, and then say nitrogen in any residual. I've made the diagonal entries of what the PDB label is, just for comparison. And then the off diagonal entries will be the strength between them two residuals. So say if you go one off diagonal, step 1, step 2, step 3, step 4. So for example, this section labeled alpha helices, you can see in the step 4 we have quite strong probabilities of hydrogen bonding. This is what we'd expect to see for a helix. As I said before, there is hydrogen bonds between residual I and I plus 4. If we move across, it's just a massive grid of now continuous probabilities compared to these discrete labels that are given. You can see here, we see helix labels by PDB, but we see little strength in the step 4 space at all. I wouldn't say this is a helix. We'll get on to that section. So there's an example. That's that section. So this whole section here, from 48 to 61, so 48 to start here, is labeled as a helix. And you see this bit here, which we don't see good bond probability. This is actually down as all being one helix here. Doesn't really follow that coil shape we'd expect to see throughout. It's just one of the sort of inaccuracies you'll see. Oversimplifications. And then there's a sheet, so you won't see a diagonal of strong bonds, you'll see bonds between different chains as there's big gaps. They look a bit different. Does anyone have any questions about any of them?
Sorry, the numbers, are they your predicted strength using the strength?
Yeah, so that's a scale of 1 to 100. So it's actually, yeah.
So where's the sort of actual data in that sheet about hydrogen bonding? You refer to sort of like
This is the data. So the entries are the strengths of hydrogen bonds between residuals.
You compute the strength from the data
Using the formula before, where you take the position on the graph and compare it to the peaks.
So Jack, you take just PDB files from the MMC files from the PDB data and take XYZ coordinates and use the formulas, right?
Yeah. And then future work, so that's what we're up to at the minute. We've produced the M by M files, which are pretty nice to look at. There's a lot of work to look into them. You can start to estimate the stability of a helix by summing the bond strengths between the step 3, 4, and 5 strengths, which is the I and I plus 3, 4, and 5 diagonal entries. That could be something, but that's not yet been looked into. And you can also sum the strength of residuals. So that would be the sum of each row in that n by n matrix, you see, to get a single vector of length n. And you can compare this to the secondary structure labels here with the total strength. But again, that still needs looking into. But these graphs are similar to the ones Olga and Jeff produced, where you have residuals and it just goes up and down, and then you could use it as comparison to compare chains, which we get on to the next thing. You could then use the total strength of each residual as a means of maybe comparing structures, rather than maybe comparing the distances and the torsion angles like before. You could use the proposed bond strengths to compare a protein and look for similarities. And that's summary. So the secondary structure labels are often inconsistent. DSSP and similar methods rely on hydrogen atom positions, which are poorly resolved. We introduce a continuous geometry-based measure of hydrogen bonding. Heat maps reveal a recurring hydrogen bonding region across all step sizes. A hydrogen bond strength function was defined to quantify these bond likelihoods. Strength matrix provides a global view of hydrogen bonding in a protein. And future work is the helix stability and comparing proteins by the stability profiles. And I'd just like to say thank you to AI Chemi for the funding to continue this work over summer. And obviously thanks to Olga and Vitaly for the continued support. And there's stuff. Yeah.
Okay, thank you. Recording.